Thanks, Benjamin. I'm happy to be here. I'm happy to see all the smiling faces. I'm wondering why we're not hearing cheers. More cheers. But here's the topic: proofs as processes. But actually, I'm going to do the following. I'm actually going to, first of all, present new results about the completeness of intuitionistic first-order logic, because it builds on everything we've heard so far, and it's also a good introduction to the topic of proofs as processes. So that's the first lecture. This one and probably half of tomorrow is really just building on what you've already seen. Then the other topic I'm going to cover, sort of with everything else, is looking forward to what might be happening in type theory. Where is the subject going, and why is it incredibly exciting? Also, as one of those themes, because this is the 100th anniversary of Turing, I will mention some of Turing's contributions here, and also some of Church's contributions. I don't know whether Bob Harper expressed his opinion to you, but he and I share this view that Church is one of the unsung heroes of computer science. Did Bob manage to stick that in this lecture? Okay, well, he and I have this strong feeling about him. I was an undergraduate student of Church and actually knew him, but he was not all that liked by his department for various reasons. And I think it carried over to people saying, well, Gödel, for example, didn't like the lambda calculus and said, you know, this isn't a good model of computing. And I think Gödel had such a reputation there at Princeton that whatever he said, people just believed, you know, okay, that must be it. These lambda terms, they can't be understood. So I'll weave in some stories. I think I'm in a good position to do that because I've been thinking about type theory before most of you were born. All of you were students. My first article on this was in 1971. Maybe it was 91. And it's just gradually taken over my life. So that's a warning to you. This is a very serious topic. I mean, it really, I was a complexity theorist first, and this has just taken over my life. So we'll talk a bit about history here. Well, one of the reasons I want to mention some of these historical figures is that the subject of type theory has been built by computer scientists, logicians, and mathematicians. And that kind of representation is what you see in the summer school here. You're going to hear from Steve Adi, who's really a mathematician. There's Steve. Benjamin and I and Bob and Frank were computer scientists. But I was really educated. My PhD was in logic, so I'm partly a logician here. It's that combination that's made type theory what it is, and I want to point that out. And of course, it has made it into something pretty amazing, as you're starting to experience, I think. Just consider the broad international uptake of COC, the system you're all loading. You know, imagine a summer school where they say you have to download this theorem prover, this type theoretic theorem prover. You say, what? It's not ML. You're not asking us to load Java, ML, but a theorem prover. And then look at the accomplishments of it. So the definitive proof of the four-color theorem was by Georges Gampier in COC. Right? That is the end of the story. There it is now, a 100-year-old problem, solved, done, stamped by Gampier, one of the masters of driving theorem provers. Okay, and then what did he get for that? Well, Microsoft Research said to him, what do you want? What do you want to do next? Go for it. He said, I'd like to prove the Fate-Thompson theorem. They probably didn't even know what it was, to tell you the truth. And his manager, they said, well, what? He said, it's a famous thing, 255 pages of mathematics, and there are questions about it, and I want to resolve. I know his manager, by the way, since I had a lot of dealings with Microsoft. They really didn't know exactly. But they gave him 10 people. Go ahead, take 10 people and prove that theorem in court. And they're almost done, right? This theorem is probably going to be finished before Christmas or something like that. Maybe George will pick a particular day. I was hoping that on July 14th he would have done it. Like, okay, there it is, Bastille Day, we did it. But, okay, so then they also, in Nijmegen, in Berenberg's group, they proved the fundamental theorem of algebra. You're going to hear about one of the major practical applications from Xavier Leroy. You'll hear about the CompCert compiler for C-Lite. This is a compiler that's extracted from a proof that you can build a compiler. Right? This is like amazing. And now the Fields medalist Vladimir Voevodsky, he's turning everything upside down. He's proving his results in algebraic topology using the Koch prover and doing it constructively. He's doing his work constructively with his prover. And Voevodsky, by the way, is not just an ordinary Fields medalist. He is one of them, but he's one of the youngest, and he's considered one of the most abstract thinkers in all of mathematics. Before they could give him his Fields medal, they had to say to him, Vladimir, would you please write up all that stuff you did on the classifier, put it in a little book so we could give you the Fields medal, which is not like the Nobel Prize, right? It's even more selective. Every 4 years they give it. So Voevodsky dutifully wrote up the little book, and then they gave him the Fields medal. And so here he is, one of the top mathematicians in the world, and he's deep into constructive type theory. And I'll tell you, this gets people's attention. Maybe life shouldn't be that way, but it is. In my life at Cornell, I'm hearing every day about Benjamin's work at Penn. They're telling me, why aren't you using NuPro to teach the programming language course? Look at his book on software foundations. Look what he's been able to do. And I said, okay, he's actually a grand student of mine, and I'm proud of him. And I say, yes, he's doing great, but do I have to actually compete with him? Well, you think you should do this. And then DARPA, the Defense Department's Advanced Research Agency, they're worried about cyber warfare. You see this in the news every day if you look around. Drones being taken over, right? Police drones being taken over. They're scared to death about this. And they've put a lot of money into verifying protocols, verifying the security properties of systems all the way from drones to just cloud computing. The military doesn't want to put their systems in the cloud because they think it's not secure. Okay, so what are the proof of systems that the U.S. Department of Defense what's the one they use the most? Koch. That's what they use. I try to tell them, that's a French system. It's not a good one. But the French really support this incredibly well. And they have these amazing industrial applications. The Java card is the only smart card. We can't in the United States do what you can do with a Java card, right? It has all your personal data on it. You can stick it into the bank, and they won't know your medical history because the Koch guys proved that those domains are separate. And I don't think Americans would use these cards if we have it, because we don't trust any bank. We figure the banks will invest more money to crack those codes so that they can see if you've got a debilitating disease and then not loan you any more money. Then the government can invest in protecting us from the bank. So Americans won't use this. But we do use the Airbus and the flight control software in the Airbus verified by what? Koch. Okay, and there are many thousands of Koch users. I was trying to get a good number here, and when I was meeting last with a Koch group, I asked them, what do you think? Do you have 10,000 users? They said, well, they wouldn't want to say. They have 1,000 1,000 registered users who really use it seriously, and they're teaching 5,000 people a year, so who knows? But there's a lot more. Okay, but another thing to think about in this setup is what do these Coq programmers learn? I think of Coq as a programming language as well. So you know that expert programmers, they love to get down into the details of their programming language. The more arcane the language, like C, the more they love to get down into the little details so that they can use some flaw in the compiler to get their work done faster than anyone else. But what do you learn when you learn Coq? You learn about mathematical types. You learn inductive types. You learn what a proof rule is. You learn realizers. You learn formal semantics. You learn classical versus constructive logic. This is the kind of thing we'd like programmers to know. And that's what they're getting in Coq. And the other thing, it's all in a unified theory of computing. Right? They're not just getting it as, here's the manual for Coq. This is about the theory of computing done constructively. And also for the United, to tell you something positive about education in the United States, I just found this out recently. We've developed a common core mathematics curriculum for the entire country. That's never happened before. All 50 states are going to teach the same stuff. And it's not going to be set theory or the new math. They're going to teach algorithms. They're going to teach data types. And they're teaching computable functions to pre-middle school students. So now you can imagine what will happen if we've got a Coq-like programming language that the government, that we get interested in, the education. It could be that education in the United States will start where these 7-year-old kids know type theory rather than set theory, which doesn't, and it's going to be useful to them. Okay, so anyway. Unified idea is plausible. And by the way, if you take the union of Coq, NuPerl, and MetaPerl, we cover a heck of a lot. You've seen what we cover in programming languages. You'll see from the NuPerl side that we cover, we're going to cover systems. And actually, NuPerl and Coq are very closely related. The inductive types are based on a PhD thesis of Max Mendler, who was one of my PhD students. We share the tactic mechanism of LCF. We all share that. And a lot of the code for Coq 8 was written by Chetan Murthy, who is, again, a Cornell grad, but one of the best programmers in the world. He's the guy, he's a freelance, he works for IBM, but they let him do almost whatever he wants until there's a hard problem in the world. And then they find out where he's living and what he's doing. And they say, all right, Chet, we need you. Bank of America is about to crash. He's an unbelievable programmer. And that's behind all of these systems that you're hearing about. Coq, NuPerl, MetaPerl, HOL. There are amazing programmers who make this stuff. Okay, so maybe that's enough of all this stuff. But here on Turing, by the way, one of the things Turing foresaw, and it's articulated very well by Hodges in his science article on Turing. Hodges says Turing knew that the universal machine that he developed put logic, not arithmetic, in the driver's seat. Because the Turing machines compute on symbols, right? They're symbolic computing machines. So that's one thing that Turing knew was going to happen. The other thing is he was very interested in type theory. And one of his first papers, 1948 paper right after the war, was on a practical form of type theory. And believe it or not, in there he used Church's simple theory of types with a lambda calculus. That showed he was brave. He finally went against the girl. And the HOL guys should love this because that theory, Church's simple type theory, is HOL's type theory. So Turing would have perhaps been using it. Okay, so now here we are at a school that brings everybody together from these different areas to a math to study what I think is the most exciting topic in computer science. Now you might say, well, what is there to be done? Look at all this great work, Conk is well established. Why should you guys be just learning what other people did? You want to start something new. Well, let me tell you that there is a lot to be done. The theory is far from over. None of the type theories that are out there is the one that we're going to see 10 years from now. So let's look at just one issue, the one you've heard a lot about, this realizability semantics. And I like Kurion's term for this. I also call it realizability semantics. But it has these other names: propositions as types, proofs as terms, proofs as programs, programs from proofs, evidence semantics, Curry-Howard isomorphism, and Brouwer-Heiting-Kolmogorov semantics. Those are all synonyms for the same idea. That should tell you that every camp has its own view of it, and that it's a fundamental idea. Okay, so this is good. Even my colleagues, but let's see how many of you are comfortable with it. You've seen it now for a couple of days, and I think it is one of the ideas familiar to many of you. But how familiar is it? How many of you think you could now teach this semantics under one of those names to second-year undergrads in computer science? Whoa, should have been bigger number. But at least, okay, 5 or 6 of you. I took this poll at LIX, and well over, that's an audience mainly of professors and PhD students, finished PhD students. Well over half of the 200 people listening said yes, they could teach it. Okay, so I think it is, and I hope at the end of this, you guys will say, yeah, I could teach this semantic. So let me, so you know what it is. I think I won't take much time. You all know what this propositional evidence is, right? That the evidence for an AND of propositions A and B is the Cartesian product of the evidence for A and the evidence for B. Everybody knows this slide? You've seen it 100 times, right? Okay, we're going to go into that in more detail. There it is in another font. I wasn't sure this font was print. Okay, so there we are. I tend to use this notation for the dependent, for the existential quantifier. I say that the evidence for
I think it might be worth actually talking through that slide, since
sure.
The way it's been talked about in the last few days has been using a little bit different notation.
Okay.
So I think there may be
okay,
people in the room that understand it better than they think they do.
Let's go back to it. So when I teach this to undergrads, especially when I get down to the meaning of implication, they all just get it. Whereas when you teach classical logic and you say A implies B means not A or B, they scratch their heads and say, what are you talking about? That's not the way they learn it. But what do we teach them about the meaning of A implies B? How many of you know that? Well, I won't call on anybody, but how many of you know that? So what do we tell the undergrads? We say the evidence for A implies B. The evidence, the semantics, the meaning of it is there is a function that takes evidence for A and maps it to evidence for B. And one reason computer science students like that is they've already confronted early in their education theorems that say something like, if graph isomorphism is solvable in polynomial time, then SAT solvable. If the extended Riemann hypothesis is true, then SAT is in polynomial time, right? They get theorems like this, where you don't know the truth of either the antecedent or the consequent. So you say, you tell them, if the extended Riemann hypothesis is true, and you write that up, you say, then SAT is in polynomial time. Now, we don't know whether the extended Riemann hypothesis is true, nor do we know whether SAT is in P time. So you can't do a truth functional semantics, and they know that. We don't know the truth of either one. But what we're showing them is if somebody gave you evidence for the Riemann hypothesis, extended one, being solvable, you could convert it into evidence for SAP being in P-type, right? So this is something computer science students really get. The one thing that is hard to get here on the bottom is what does not A mean in the semantics. And what it means is there's no evidence for A. And there are a number of ways of saying this. One of them is to say, okay, if we had evidence for A, this is the very bottom thing there, then we would get evidence for false, that's the empty type, and there is no evidence for false. But by the way, Brouwer, who invented this semantics in 1907, right? Just at the time when logic was at its peak, when Bertrand Russell and Alfred North Whitehead were writing Principia Mathematica, there, sitting over in Amsterdam, was Brouwer changing the meaning of all the quantifier, all the connectors. He changed them from true functional semantics to this. Okay, so now we're starting to see, gee, Brouwer had a pretty good idea. That's a good semantics. And the one that you all probably heard about is Brouwer's interpretation of evidence for A or B. All right, so the evidence for A or B is the disjoint union of the evidence for A and the evidence for B. And the disjoint union has the property that you can tell which disjunct you're in, right? That's why we call it disjoint union. So what Brouwer said is if you know A or B, you know which one it is. You know A or you know B. And this got him into big trouble. At first, he was very quiet about this stuff, by the way. He wrote that in his PhD thesis. He got it accepted, even though his advisor said, oh, could you tone it down? Why do you have to be so in the face of everybody else? So he did tone it down for many years. He was very patient about this. I think his advisor, you should pay attention to your advisor on a little comment, but his advisor probably said to him, he didn't call him by his first name. They called him Bertie. That's what they called him. He said, Bertie, whatever you do, don't talk about these ideas until you have 10. That's probably what he said. And so, and then he translated that as until you're the best mathematician in the world. And he set out to become the #1 mathematician in the world. And I think in a period of 4 years he published 55 papers, something like that, and invented all of point-set topology. There it was. He created a brand new subject. And then he said, okay, now I'm going to start talking about this. And sure enough, he got into big trouble with Hilbert. And then provoked a lot of controversy. But now it's not so controversial. You can believe in this and you'll still get 10. In fact, it might help you. Some university. Okay, so now for the existential quantifier, in America, this goes over very well. When, in Missouri, anyway, because there, if you say to somebody, there exists an object such that you describe its properties, they say, show me. That's called the show me state. Show me one. Okay, so that's the Higgs boson. Why spend billions of dollars? They got to show these guys in Missouri where is the Higgs boson? So they found it. So that's what the existential quantifier means. You've got a thing. So the evidence A cross B of X is you give the thing A. You actually produce an object, and then you produce a witness that the object has the property. That, I like to call that thing a dependent product. Yeah.
So why, usually we would think of the sum as the dual of the product.
I was just
Okay.
about to say that.
Okay.
The category theorist Steve is probably squirming and everything. Why is he doing this? But look, it's a product type, right? It's a product where the second component depends on the first one. So it is, if you say it's a dependent product, nobody, well, unless they've learned the other semantics, nobody argues with you. It's a pair. Okay, so I mentioned earlier in the body. You can also see it as a disjoint union over a family. And then you know which element it's in. which is the DX. Okay, so I'm going to call it, I'll try to avoid calling it anything. The evidence for the existential part. So here's a very simple example of this. Let's say we have A and B implies C, implies A implies B implies C. Have you all done this exercise already? Right. This is the currying thing, right? And out comes a realizer in that semantics, because we see that the evidence has to be a function that takes the evidence for A and B implies C, then it takes the evidence for A, and it takes the evidence for B. So you've got lambda F, lambda X, lambda Y. You've got all those functions there, and then it produces evidence for the C. Okay, again, undergrads get this after a couple of lectures. Now, what we're going to do is, you've already heard a bit about how we do the typing there and how we could convince somebody that this is evidence. So if you wanted to convince somebody that you had the right evidence there, you could do it by giving a proof of the proposition and extracting the evidence. So in the proof, you would have an assumption that F is in this type, X is in A, Y is in B, and then you see you're just applying this function F to the ordered pair of elements X and Y that are indeed from A and B, and the result of the function will be something in C, right? Everybody should think this is, yeah, right. Okay, so that's what's going on here. And you could think of this as the specification of a programming task. For when you're teaching undergrads, you say to them, you can say to them, that's a spec for a programming task called currying. This is what currying has to do. It takes a pair and turns it in a function from an ordered pair to a function from the arguments given sequentially. Okay, so we're specifying a programming task, and then the evidence term there is the program that satisfies it. I hope you did. Did you do the uncurrying also? Yeah. Good. I'm going to give you a harder exercise before the end of the lecture. You'll see some hard ones. Okay, but here's the challenge. Here's what I experienced now that my colleagues, all of them, even the people who hated the lambda calculus, they've heard so much about COP. They've seen so many lectures in colloquia about COP where the dreaded lambda term appears, and many of our theoreticians who were in the girls' school, they hated lambdas, but now they say, oh yeah, I see, this is just like a functional program. Okay, they finally get to understand the idea. They get enthusiastic about it. And then they always ask me, it's inevitable, you can see when they've got it, but when they come by to ask me this question. They say, yeah, I've been reading up on this thing, and I want to see the completeness proof for first-order logic using this semantics, but I can't find one. You just give us Kripke semantics, and that's not this semantic. So where's the completeness proof for first-order logic, or even propositional logic? The ones who get frustrated first come to me with that. They say, for propositional logic, you don't have a completeness theorem for your semantics. So what's wrong? And for years, I would just say, well, what I knew was we couldn't find one. We've been working on it for a long, long time, the whole community. Couldn't get the proof. So the first line of defense here was to give excuses. We'd say, well, completeness isn't all it's cracked up to be. You really don't need completeness. They didn't buy that. They would say, how come every logic book I go to the library and get off the shelf, or I borrow from you, every single logic book does completeness? But you don't. And then we tell them, there is a completeness. We say, what? There is a completeness proof for Kripke semantics. And they say, what the heck is that? They actually do know what that is. So the only semantics we could give them was the semantics for Kripke version of this logic, which is not the semantics you've been learning. And we're not going to teach that to you, right? We're not going to teach Kripke semantics. That isn't the intended meaning. and you don't get computational, you don't get programs out of it. Okay, so I'm going to show you that finally we have the proof. We can give you a constructive completeness proof. I'm going to give it to you. And you can look up our paper on it. It's in the archive. It's being refereed now because we just got this result. My colleague Mark Bickford and I were very happy about it. That's why I stuck it into this lecture. Because I think you will understand it. You will see the idea. Okay, so that's what we're going to do next, right now. We're going to look at this constructive completeness theorem, which is a brand new result. It's one that you will understand. It's a constructive proof of completeness. So with it comes an algorithm that will take evidence and give you a proof. And for you guys who are having to do Hawk proofs and all that, this is really good. So you could execute that algorithm if you had Newport, but you didn't require that for the course. But one of the examples I'm going to do for you, we ran, it was so hairy, I had Mark run it through Newport, and I know it works. So I'm going to show you that. And then, because we're doing some new math here, we're going to see some issues in type theory design. Because you can't do this in Martin-Loff type theory as it stands, and you can't do it in COP. You have to fix those a little bit, but in the right way, in ways everybody would want to fix it. You can do it in Newport. We did it in Newport. Okay, so let's actually make sure, how many of you know about the completeness theorem for classical first-order logic? That's good. How many of you could prove that? Not too bad. I'll show you. From this proof, you'll see a really cool proof of the classical theorem. But it's in almost all logic books. And there are some proofs are really elegant. And I brought along a book that I absolutely love on this. This book, I don't get any profit for selling it. It's dope. This is the best account of Gödel's completeness theory you'll ever get. This book is unbelievably elegant. And the reason it's still in print is I was teaching out of it for years, and then Springer dropped it. And my colleagues and I convinced Dover to publish this thing. So,
what's it called?
Pardon?
What's it called?
First order logic. Real simple. And everything in it. I lectured about this last year.
Who are the authors?
Only one, Smulyan. Raymond Smulyan, student of Alonzo Church's, a famous magician, and he's written all kinds of books on logic. He probably has 10 really excellent books on logic. This is his best, but his other ones are also really great. Yeah, so I highly recommend it. This used to cost $5.
It's $6.50 on Amazon right now.
Probably the cost of paper or something. Anyway, so what that proof does, the reason it's in all the logic books, is it connects semantics, like the meaning of truth, to proof rules. And that's considered a very fundamental thing. So you would think it would be fundamental in the intuitionistic case, but why hasn't there been, well, I guess I'll tell you that in a minute. Let me just indicate to you that this was done by Gödel. I just looked up the date. On July 6, 1929, before the stock market crash. Gödel wrote his dissertation called On the Completeness of the Calculus of Logic, and already by 1930 he published it. And he used the axioms of Principia Mathematica to give his proof. And I've read his original proof. You couldn't even teach this to graduate students. I mean, it's really, really hard. Okay, so here I advertise Smulyan's book. I was premature in grabbing the direction, waited for the slide, and then you would all know the author and publishing date and all that. Okay, so what did he say? The theorem says that there is a set of inference rules for first-order logic, in particular the ones that Russell and Whitehead gave, that has the property that any sentence that's valid, that is true in every model, is provable by these rules. And I don't think he was setting himself up for his very famous theorem, right? Gödel is famous for his incompleteness theorem. How many of you know that? Yeah, so everybody knows that. I mean, so his incompleteness theorem is about arithmetic, and it says you can't get this kind of completeness if you go to piano arithmetic. But for first-order logic, you set up the semantics like this. The semantics requires that you define a model. What is a model? So for first-order logic, a model is a domain of discourse, the object you're talking about. And then you have only atomic propositions, mapping, say, from n-ary relations into Booleans. So that's all you've got, a domain and an n-ary relation, and sometimes the structure there, where you've got the domain D and all these relations, any finite number of them. We call that a Tarski structure because the semantics you give for the connectors and or not implies for all that exists are the standard classical ones, right? So the semantics of there exists is actually that you've got a classical argument that something exists. You don't have the pair, you just know the exist statement comes out true in the model, but you may have a very non-constructive proof of the witness. So this ought to be, I hope this is pretty clear, right? It's first-order logic is just about relations, primitive atomic relations, connected by and or not implies and for all and exists. And you'll see the rules for them in just a minute. Okay, so the classical method of proof goes like this, by the way. What you say is,